Has it started yet? Sorry. Are we good to go?
Yeah, go.
Okay, great. Okay, well, I'd like to thank the organizers for inviting me to speak. So I'm going to tell you about some work that hasn't appeared yet. It's with the student Min Lee and with some discussions with my postdoc, Anthony Speranza. The title of the paper will be Asymptotically Isometric Codes. So, I mean, the essential idea, let me summarize it really quickly, is to try to think about sort of this quantum error correcting paradigm for ADS CFT or holography more generally. And to think about that very sort of more precisely than is usually considered by thinking about sort of a family of CFTs with a large n limit, and then taking that seriously. So before I get to that, I'm going to first introduce or remind you what this quantum error correcting story in ADS CFT is, the old story at least, and then I'll discuss how we sort of improved it. Okay, so the old story starts with the following observation that you can think about ADS CFT in particular. Maybe to start with, you just think about ADS CFT in vacuum as dual to ADS with some small number of excitations about ADS. You take those small excitations, say by acting with operators in the bulk, and you construct a Hilbert space. Let's call this H here. And you think of the ADS CFT map as a map from the bulk to the boundary, but it's one in this case because we've constructed this Hilbert space by acting with sort of a finite number of operators. It's a map between a finite dimensional Hilbert space H and the boundary CFT Hilbert space K in this case, which is the full sort of CFT Hilbert space. In this case, the construction has a finite dimensional bulk Hilbert space. Just in this paradigm, and in particular, that means that the code that you're going to get from this, the quantum error correcting code, has a finite dimensional code subspace. Okay, so in this paradigm, this map V is an isometry. So that what does that mean? It means that V dagger V is one on the bulk Hilbert space. Conversely, VV dagger is a projection operator in the boundary Hilbert space. It's a projection operator that effectively projects onto the code subspace. The reason these authors took the code to be a small Hilbert space was because they were worried about black holes forming. So if you act with enough operators, you're going to form a black hole, and information is going to get lost inside the black hole. So to not worry about that, you work with these small codes. Now, in this setup, you can compute entropies, and you can give a picture of the Ru-Takinagi formula, which is central to our understanding of ADS CFT and quantum information in ADS CFT. So we know, in vacuum ADS, this is a time slice of ADS. We know to compute the entanglement entropy between two boundary regions A and B. So if you take say the vacuum and you compute the reduced density matrix for the region A and you compute its entropy, to compute that entropy, the rules in ADS CFT is to find the minimal surface. This soap bubble falls into the bulk and ends on the boundary of the region of A. So that's this RT surface. And so that's just some computation you can do. You can compute the entropy, but the nice thing that ADH, this original paper on quantum error correction pointed out was that there's now an interpretation of what that Ru-Takinagi surface is doing. In particular, the Ru-Takinagi surface is now splitting the bulk into two regions. Okay, so the two regions are little a and little b. And in particular, let's just assume that the bulk Hilbert space, which is this finite dimensional Hilbert space, now has this tensor product between those two regions, HA and HB. And the point of the interesting point of these codes is that you can now try to reconstruct the information in this region, little a or little b, from the boundary regions, big A and big B. In particular, the information in little a, so over here, is protected from erasure of the entire boundary region B. So if I do something really bad over here, there's some errors that arise over here, it doesn't matter. I can still reconstruct the information in little a. This is a property of this holographic map, this V that we constructed. You can discuss this from the error correcting point of view, and the idea is that you think about a quantum channel. So this is a trace preserving completely positive map on density matrices, where in this case, this channel is some noisy channel. It's going to give you some errors. In this case, it's taking the bulk density matrix. It maps through this isometry to the boundary. So now it's a boundary object. And then we trace over B. And so tracing over B is this erasure error. That's removing all the information in B. And that gives us a density matrix on A. And the question of error correction is whether you can reconstruct from this density matrix on A, the original density matrix in the bulk. Now, it turns out you can't construct the entire density matrix on the bulk, because that would be acting everywhere in the bulk. You can just reconstruct the information in little a, okay, which is what we expected in any case. So that means there's another quantum channel that acts on this row A and gives you back the density matrix on little a. Okay. So it inverts this noisy channel, at least on this subregion little a. Okay. Now, once you have this reconstruction map for the density matrix, you can also apply it to operators in the bulk, and that's what usually defines what we mean by some entanglement wedge reconstruction. So let me define what that is. So if I have my reconstruction map R, I can take its sort of adjoint, and so the adjoint R acts on density matrices, but density matrices are just a way to compute one-point functions of operators, right? So we usually take the density matrix and then we trace it against operators. So that means the adjoint of this quantum channel actually acts on operators. And so in this case, it acts on a bulk operator, phi little a, so in the bulk region little a, and gives me a boundary operator, OA. And this boundary operator has the property that on the code subspace, it acts like this bulk operator phi a. So we've managed to reconstruct the bulk operator phi a as a boundary operator on this region big A. Okay, so there's an operator on A whose action is the same as phi A on the code subspace. Okay, and so this is what we understand as entanglement wedge reconstruction. Another interesting observation in this paper by ADH was that this sort of reconstruction map has some very interesting properties. In particular, if I have two boundary regions, A and B, and let's say they're overlapping like this, then you expect to be able to reconstruct just with one of them, this region in here, and just with the other, this region in here. But when you combine them together, you can now compute another Ryu-Takayanagi surface, which is actually bigger than the combination of the two. And so that means you have new information that you can reconstruct, which is not just a simple combination of the information which was reconstructible from A and the information which was reconstructible from B. You get this extra region. So that's this triangular region over here. Let me try to highlight it, this yellow region that I'm highlighting here. And so this is some version of quantum secret sharing. It's some information you can only get if you have access to both A and B. So why is it that the Ryu-Takayanagi surface delineates this region where we can do entanglement wedge reconstruction? So this is a special property. If I just gave you some random V, this isometry, it wouldn't satisfy this reconstruction property, but it's a special property that happens in these codes. And it's something you can prove. And the reason it's the Ryu-Takayanagi surface that delineates where the information is available is that sort of where entropic quantities are defined. And in quantum information, you can often prove things like whether you can do quantum error correction based on entropic quantities. So that's sort of a hand-wavy way to see why the Ryu-Takayanagi surface is so important, because it's the thing that's computing the entropies, and the entropies are the things that are determining whether we can do error correction. So that's hand wavy. There's a much more precise way to think about it in terms of this object called relative entropy. In particular, relative entropy is just some quantum information quantity that compares two density matrices. So if I give you two density matrices and the relative entropy is 0, you know that they're exactly the same. And so it gives you some measure of the distinguishability between these two. And it turns out that if you can show that the distinguishability between two states in the bulk under this sort of holographic map, this noisy channel that I just constructed, is the same on the boundary, that's the equality of this relative entropy. So the distinguishability doesn't change at all under this map. Then if that's true, you can prove entanglement wedge reconstruction. You can prove that you can find these operators. You can find this recovery map R. And in ADS-CFT, this formula was proven by JLMS, Jaferis, Lipowicz, Moldacena, Su. They noticed that for the Rutaki-Nagy surface, the relative entropes are equal in the bulk and the boundary. And so, this was then used to do bulk reconstruction. Furthermore, you can even go further than this. Dan Harlow wrote a paper where he showed that there's a correspondence basically between special kinds of error-correcting codes with the properties that I just discussed and something that looks like the Rutaki-Nagy formula. So that's great. This sort of picture is very interesting. It's a very nice way to think about ADS-CFT. But today I'd like to try to enlarge the paradigm. So I said that these error correcting codes, as discussed so far, work very well when you have a sort of finite dimensional bulk Hilbert space. But I'd like to enlarge it to allow for the bulk to be at least some quantum field theory, maybe some quantum field theory on some fixed background. But we know that in quantum field theory, the Hilbert space should be somehow infinite dimensional. So that means we have to change the paradigm a little bit. So why would I want to do this? Well, okay, there's various reasons. Generally we expect that in ADS-CFT, at least in some limit, the bulk theory should be some say in some semi-classical limit, the bulk theory should be some quantum field theory, maybe on some fixed or slightly fluctuating background. Also in quantum field theory, we have this sort of interesting property, and this is a property that I'd like to put in the bulk, which is that if you cut the quantum field theory into two regions, like we've been doing here, in particular now, these bulk regions that I was just discussing, little a and little b, if we cut them, then typically when you compute the entropy, you get an answer which is infinity. Okay, and why is that? Well, in quantum field theory, you have sort of infinite short-range correlations between regions, and and those correlations persist on all scales, and because of that, you get divergent entanglement entropy. Typically, to deal with that, you cut off the entangling surface. You pick some small region to cut off where you're computing the entropy. But in reality, we should sort of confront the fact that you have this infinite entanglement entropy. And what that tells us is something interesting about how we should think about quantum field theory and sort of local regions in quantum field theory. So in particular, because of this fact that you have infinite entanglement, the Hilbert spaces actually don't form this tensor product, HA tensor product HB for these local regions, A and B. Rather, what you should think about is you should think about the algebra of operators associated to these regions. So, you could still do this if there was a tensor product. You could still think about the algebra operators associated to regions. It's just all the bounded operators on HA or all the bounded operators on HB. But in general, when you have this sort of infinite entanglement for all states, that actually means that the algebra of operators cannot be thought of as in the standard way that you would think about bounded algebra of operators, and you have to sort of enlarge your paradigm and think about more general von Neumann algebras. So if you think about just bounded operators on some Hilbert space, that always defines something called a type 1 von Neumann algebra. But in general, in quantum field theory, because of this issue with entanglement, the type of von Neumann algebra you get is something called a type 3 von Neumann algebra. So this is something that algebraic quantum field theory people have thought about for a long time. They've thought about, what kind of algebra of operators that we should assign to local regions in quantum field theory. And based on lots of work, they've realized they worked out that in fact the appropriate von Neumann algebra is this type 3-1 von Neumann algebra. This has the property, indeed, that you cannot write the Hilbert space as a tensor product like this, HA, HB, and it also has the property that all states have infinite entanglement entropy. So this is what we expect. So this is at least some sketch of why that's true. So just, for this talk, I'm not going to define those concepts very carefully, but you should just keep in mind that sort of type 1 von Neumann algebras are the ones that maybe you're used to thinking about. And type 3 are these fancy ones that arise in quantum field theory due to this infinite entanglement. So this is something that I'd like to put in the bulk. And another motivation for this, and it's not working. Let me try. Sorry about this. Let me try to disconnect. Okay, let's try this. Oh no, this is not going to work. Still not working. Okay, just a sec. Sorry about this. Let me just disconnect. I'll connect in a second. Yeah, so basically, I want to have an error correcting code where the bulk has this quantum field theory like Hilbert space, which is infinite dimensional and allows these non-trivial sort of type 3 von Neumann algebras. Yeah, I just disconnected my iPad for a second.
All right. Okay.
I need to reconnect my pen. I'll reconnect it in a second. Sorry about that. Okay, there we go. Yeah, so I want to have this setting. And one reason for that is I'd like to study sort of more interesting details of quantum field theory in the bulk. In particular, there's energy conditions in quantum field theory, like this average null energy condition, the quantum null energy condition, which are interesting, but often you can only really prove them in this setting where you have these non-trivial type 3 von Neumann algebras. And so I'd like to incorporate that physics in the bulk. In particular, we know these energy conditions are very interrelated to gravity in the bulk. So if we want to understand what they're doing in general, then maybe we want to use ADS-CFT. But if we're going to use ADS-CFT, we sort of have to confront this fact that we need these non-trivial von Neumann algebras in the bulk. Now, having said that, that's what I want. There's some issues. There's some obvious issues. This Hilbert space is too big. That was sort of the original motivation for doing this error correcting code. You have small Hilbert spaces. And in particular, one way to understand that is that due to these two sort of general holographic bounds, you expect a gas of particles in a gravitational theory, at least when the energy density is large enough, will collapse and form a black hole. So in general, that means that if I, think about the Hilbert space of quantum field theory seriously, then there are states in that Hilbert space which actually may not have a sensible gravitational dual. And and so, there's some issue there. The other thing is that this whole story I told you about entanglement entropy being infinite, in a gravitational theory, it's not actually infinite, it's finite. So you have typically some quantum field theory divergence, but that's absorbed by that's absorbed by some renormalization of Newton's constant, and you also have this area term, area over G Newton, and in particular, typically you expect, you always expect that the total thing is some finite entropy. So perhaps we shouldn't have expected these non-trivial type 3 von Neumann algebras to arise at all. And so, but still, I'd like to sort of forge ahead. So I should mention that there were previous attempts by Kang and Kolchmeyer and some work by me, where indeed you could do this quantum error corrected paradigm with non-trivial von Neumann algebras. But we had to assume that the quantum error correcting code was exact. So that means it's sort of, there's no approximations, there's no errors. Well, the code itself has errors, but there's no, the paradigm has no reconstruction errors. And when we did that, we assumed some fixed but large n. And as I said, we managed to produce error correcting codes with these non-trivial von Neumann algebras. But having done that, there were some sort of glaring issues. So let me explain what some of those issues are. So firstly, the codes that we produced that certainly had could have type 3 von Neumann algebras in the bulk, but there's some sense in which maybe the type 3-ness that we got was not actually a bulk effect. So as I said, if we're at finite n, you expect that the actual entanglement entropy locally at this RT surface, so this is sort of a schematic picture of the bulk here. This is say A and B. This is A and B. And so you expect that there's sort of some entanglement near the RT surface, but at finite n, that entanglement actually is not infinite. Now it could still be infinite overall just because of divergences near the boundary, right? So these are UV divergences in the quantum field theory, and in fact that's what usually leads to the type 3-ness of the von Neumann algebra in the boundary quantum field theory. So indeed this could still be true, and we're just not capturing this physics that I wanted to capture. The other issue was kind of a big issue, which is that you can prove based on some general assumptions in these codes that the additivity property that I mentioned for these overlapping regions, the fact that you have this sort of non-trivial region that arises, this triangular region, actually does not occur in these codes. You can prove that this region is absent, which then just doesn't make any sense from a bulk point of view. So this was important in the original ADH story, and it's just absent when you do these exact codes with these non-trivial von Neumann algebras. So the solution for all of these issues is to use approximate error correcting codes. So that means that there's reconstruction errors. So that's believed to solve these issues. But it turns out that then, it's still really hard to work with these non-trivial von Neumann algebras. So that's what we're going to try to do today. And the resolution that we'll find, or the way that we sort of work around it, is to really think about this large n limit seriously. So in particular, that, in ADS-CFT, Newton's constant maps to some parameter in the boundary theory, which is counting the number of degrees of freedom, or 1 over that. And so when n is very large, Newton's constant's going to 0. And so when G Newton goes to 0, a lot of these issues that I was mentioning before sort of go away. In particular, these holographic bounds sort of don't become important. You never form black holes if you take G Newton literally to 0. So the goal is to have some error correcting code with a parameter n that we're taking to infinity. And part of the inspiration for this is thinking about these recent papers by Lou Leuthauser and Witten, where they were sort of discussing how these non-trivial von Neumann algebras can arise. In particular, in their case, they were thinking about sort of black holes and the thermofield double state. You can get these non-trivial von Neumann algebras arising in these limits as n goes to infinity. So then, as an additional goal to this, I'd like to generalize this Lou-Leuthenauser work beyond these Sommerfeld doubles and black hole states to just general entanglement wedges, and in particular to this quantum error correcting paradigm of holography. So I'd like to sort of unify these things. Okay, and so the idea is that to do that, we should introduce a new kind of code, error correcting code, and the name for this code that we've given is this asymptotically isometric codes. And let me start with a definition of what this code is. And it may seem like there's a lot of things that I have to define, a lot of definitions. But I also claim that this is something that you can almost derive out of thinking about some matrix model like SUN gauge theories, or or more specifically n equals 4 super Yang-Mills theory at large n. So this is something you can sort of essentially derive with some technical assumptions that I cannot derive. So there's some assumptions, but the structure that you get out looks, it essentially comes from thinking about these theories. So to define this code, I have to think about the boundary theory in ADS-CFT as a family of theories. So there's a CFT and there's a parameter on that theory that I'll call n. That CFT acts on some Hilbert space, and because it's a CFT, it's very natural to think of it as living on this cylinder, SD minus 1 cross R. So this is a picture of this cylinder here, where now I'm including time. And I'm going to think of this from an algebraic quantum field theory point of view. So I don't want to scare people with that. It's not that crazy. All I think of as algebraic quantum field theory from this point of view is some assignment for boundary regions, causal boundary regions that I'll call O, and algebras in the boundary quantum field theory. So these are these MNO. So they're labeled by n because there's for each n there's an algebra of operators. So these are this is sort of the algebra of operators associated to some causally complete region, which is like this diamond region or some double cone. So we're in higher than 2 dimensions. So there's some, or we might be in higher than 2 dimensions. So there's some double cone region, and that's causally complete. And so to each of these regions, we have some assignment of operators, and there's some consistency on this assignment, which is kind of obvious. So I won't mention that. Okay, and so these algebra operators are going to play the role of these regions A and B that I was talking about in the original discussion. Often in the original discussion was just done on some time slice. In algebraic quantum field theory, you really think about time and causally complete regions. Okay, so then this whole Mn refers to the net of all possible subalgebras or von Neumann algebras associated to regions. And so you should, while I'm giving you this discussion, you should think of, as an example, just n equals 4 super Yang-Mills theory, which is some SUN gauge theory, with the parameter n. Okay, so this is just the boundary theory. So you should think of this as like the microscopic theory. It's the boundary theory. Now, to discuss the bulk theory, I have to introduce a code. So this is a code in the sense of a quantum error correcting code. So the code consists of 3 elements. The first is this C, which is some family of von Neumann algebras, very similar to Mn. So it's a family of local algebras that is related to boundary regions. So given a boundary region, there's some algebra of operators acting on the code subspace. There's a map, Vn, which is like the isometry that we introduced before, but it's a family of maps because now I have to map each of the code subspaces into the boundary theory at each n. And then there's some gamma n, which are maps on operators that I'll define in a second. So, so this C is an assignment of bulk algebras to the boundary regions O. I'm going to claim that these bulk algebras are something called the causal wedge, or operators associated to the causal wedge. This Vn is a bulk to boundary map from the bulk Hilbert space to the boundary Hilbert space. And it's a sequence of encodings of these error correcting codes. And in particular, it's not going to need to be an isometry. So it's just going to be some map between those two Hilbert spaces. And gamma n are simple reconstruction maps. So these are like the reconstruction maps like R dagger. Yeah, I wrote that. And their goal is to reconstruct an operator in the causal wedge as some boundary operator in MNO. Okay. And additionally, this code satisfies the following conditions. So Vn dagger Vn asymptotically limits to 1. So it looks like it's an isometry. So if Vn dagger Vn was equal to 1, then it would be an isometry. Here, it sort of limits to 1, but it limits to 1 in a certain sense. So this is this weak operator limit. So this is a little bit technical, but it's something that arises in von Neumann algebras a bunch, is sort of how you take limits of operators. And so the weak operator limit, let me explain that, is basically you fix two states and you compute matrix elements in those two states, and you take the limit on that. And the claim is that you always get the overlap between those two states because this becomes 1. And so for any two states, eta 1, eta 2 in the Hilbert space, if I fix and I compute the matrix elements and take the limit, then I always get the overlap. So this is what it means to have this weak operator limit. In infinite dimensions, it turns out that there's a distinction between that and what you might have guessed, which is just to take Vn dagger Vn minus 1 and compute the operator norm and impose that that goes to 0. So this is sort of a uniform limit, and this is not true. Okay, so just because I have this weak operator limit doesn't mean that this is true. So in some sense, these codes are sort of isometric, but they're only weakly isometric. Right, so that's one condition on the code, and the other condition is that these gamma n maps, which take bulk operator C to the boundary, this is some boundary operator, and act in a way that it's the same as the bulk operator on the code subspace. This should be true, but it's only true in some other version of the limit, this strong operator limit. The strong operator limit is basically, instead of taking matrix elements, you just take one state in the Hilbert space and then compute the norm and demand that that norm goes to 0. So it's just some other notion of convergence. So the claim is that this sort of triple of things, sort of bulk causal operators, Vn and gamma n maps, is some interesting model that we can study in its own right. In particular, it's going to fix all the previous issues. It's in some sense approximate. We're doing approximate quantum error correction, and there's no, and as we'll see, I actually won't discuss it, but yes, there's no additivity issue with this. Okay, so right, but you know, that's you know, a claim. It's interesting in its own right. But the other claim is that you can essentially derive, up to some technical assumptions, this structure from the large n limit of some matrix model. So let me sketch that. And this discussion is inspired by the original paper, Lou Leuthauser. But basically what I'm trying to do is put some precise equations to that work and just generalize it a little bit. Okay, so the sketch is as follows. So the idea is that the bulk Hilbert space and these causal algebras C are constructed from the single trace fields in the large n limit. So we're used to thinking about, you know, large n gauge theories in terms of their single trace operators. So there's a sense in which the single trace sector or the single trace operators really only exist at infinite n. So that's where I'm going to start. And essentially, you can think of the code subspace as being built out of these single trace operators that exist only at infinite n. One thing I should have said before is that that's the code subspace, and the microscopic theory is the theory at fixed n. So in some sense, I'm taking the infinite n theory as the code subspace, and I'm embedding it in the finite n theory. Now, okay, so that's how we're going to construct the bulk. We're going to take these single trace fields. So we have these operators phi I, these fields are phi I. Sorry, my pen is giving me problems. Okay, let me just try to talk a bit about it, and then hopefully my pen will be okay. Yeah, so we have these single trace fields phi I, and you can define them in localized causal regions, right? So associated to causal regions, there's a bunch of single trace operators. So the first thing we construct is this gamma n map, and the gamma n map is a map from the single trace fields that exist in the infinite n theory to some very specific operator in the finite n theory. So for example, if our single trace field was constructed out of these matrices, I don't know why it's doing this to me. Okay, let me try. I'm going to do something. Sorry. Okay. Okay. All right. So these single trace fields are these phi i's, and there's some specific for each phi I. There's some specific collection of operators M1, M2 up to MK, and then sorry, these are these n by n matrices that live in the large n SUN theory. So, for example, if I'm studying SUN Yang-Mills theory, these might be constructed from the field strength, which have these color indices. So these are n by n matrices, and then we take a bunch of them, multiply them, and take the trace. And so that's usually how you think about a single trace operator. And the important thing about the single trace operators is that for each n, there is a unique operator like this. Okay. And one thing that's important that's going to arise out of these codes is that the number of operators that I'm sort of sticking in here to do this trace, say, is k operators, and that's fixed as I take n to infinity. And that's important because if k was of order n, then these wouldn't really be single trace operators. Okay. But by sort of phrasing everything in terms of the n is equal to infinity theory, I don't ever have this issue. Okay, so typically in these large n theories, if you have some finite n, say large enough, large, but then you have some n number of operators like this in here, so k is n, then there'll be trace relations, which mean that they're no longer single trace fields. So this structure will sort of be imposed here. Will arise out of these codes, this general expectation. Okay, so that's the first thing we do. We define these maps. The second thing we do is we need some sequence of states, and we need that sequence of states to have a large n limit. And what do I mean by that? I mean that if I take these maps that I just defined, I stick them in this state here, psi n, then I should be able to take the limit on this correlation function and get some nice answer, right? And so in particular, you can use that limit, the existence of that limit, to define a state on these single trace fields. The state just computes correlation functions of operators, or just one-point functions of operators. It just computes everything. And with that straight state, you can construct basically the bulk. And the idea is, once you have a state on an algebra of operators, you can always do this GNS construction. Sorry, I should have said a state. I'm using sort of two notions of the state of the word state. One notion is just a vector in the Hilbert space. This notion is the notion of a state in sort of an algebraic context, which is just a map from operators to numbers. Okay, so that's sort of the expectation value map. And so given that state, you can always construct a Hilbert space, basically using that state to construct an inner product. And so that's this GNS construction. And not only that, you also get these causal wedge algebras as just the algebra of these single trace operators that act on this Hilbert space. There's some representation that you get, but I'm going to sort of ignore that notation and get a representation of that algebra on this GNS Hilbert space. Okay, so then this limit now, the limit of this sort of these finite n correlation functions, limits to a correlation function in this Hilbert space, in this new Hilbert space with this state eta. So this vector state is now a state that represents sigma. And you can use that limit, the existence of that limit, to prove, well, so to firstly define, so sorry, let me firstly define the VN maps. So I've defined two things out of these codes. The final thing I need to define are the VN maps, and they're just defined using this equation. So they're basically defined by gamma n and sort of a linear representation of these maps, gamma n. And then you can show that this equation star here, so the limit of these correlation functions having a nice limit on the bulk Hilbert space, implies these reconstruction map statements and the weak operator limit of the weak operator isometric property of the code. So you can just prove that these arise. One important thing about this particular equation is it implies some homomorphism property. What that means is that these maps, gamma n, if I compose them with two operators in the bulk, C1 and C2, then they become a product of the two, but only asymptotically, only in the limit. And so what that's telling us is that these gamma maps are preserving the algebra. Okay, but they only preserve the algebra asymptotically, and that's exactly what we expect, because these are the algebra of single trace operators. That makes sense at infinite n. At finite n, it doesn't really make sense. So it really only makes sense asymptotically. Right. In particular, these single trace operators do not form a closed algebra at finite n, but as long as I take the limit, it's okay. So these are some comments. Gamma n are simple maps. There's something that I just wrote down by hand, so they're really simple. That actually gives a motivation why we should identify the algebra of these phi i's as the causal wedge. The causal wedge is usually defined as the region that's sort of causally accessible to the boundary region. So it's defined in terms of the future and the past of the boundary region O in the bulk. It's defined as the intersection of those two. And in general, it's some region that's sits inside the Ryu-Takinagi surface. So it might be this green region that I've highlighted here. So this region is an orange region. And you should sort of think of it as like everything outside, analogous to everything outside a black hole horizon. And then to get further, to get towards the Ryu-Takinagi surface, we need to extend the causal wedge, and that's non-trivial, right? That's like moving inside, like reconstructing operators inside a black hole horizon. The causal wedge is thus simple, and the entanglement wedge, which is something we're going to have to define in a little bit, is more complicated. But so far, we just have these causal wedges. Let me skip this. No, let me say something about this. So if I compute the commutant of all of these single trace operators in this GNS Hilbert space, so the commutant is just all operators in that Hilbert space that commute with any single trace operator C, then it's plausible that this thing is non-empty, need not be trivial. And in general, you can think about this, and really this should be associated to the emergence of black hole horizons. It turns out that it's a little tricky to study in general, but there's a more simpler version, which is related to, instead of thinking about all possible single trace operators, I just think about single trace operators associated to a region O, so one of these causally complete diamonds. And in general, if I think about O, this is now a boundary picture. This is a boundary picture. If I think about O on the boundary, there's another region on the boundary associated to O, which is all of the points that are space-like separated in the boundary to O. So that's called O prime. And so, in some sense, you think of that as, so those are all the fields that commute with operators in O, at least on the boundary. Now I can think about the causal wedges in this code defined associated to O. And I can also think about the causal wedges associated to O prime. And in general, there's no reason for these to, so if I take O and I compute the causal wedge of O and I compute its commutant, everything that commutes with O, but now in the bulk, that need not be equal to the causal wedge of O prime. Yeah, so this is a generalization of this thing having C prime being sort of non-trivial. And the picture is as follows. If I just draw a time slice in ADS, here's my region O, here's my region O prime, it's sort of the complement region. And the causal wedge is this green region over here for O, and the causal wedge for O prime is over here. And indeed, this is true, but you do not have equality. And the lack of equality just means you have this sort of, this region in between. And this region in between is where the entanglement wedge, the Ryu-Takayanagi surface would sit. And not having equality here in this equation is known as, this is a violation of Hague duality. And I think the idea is that in these codes, it will typically arise. And so that's interesting, but we want to do better. We want to actually get all the way to the Ryu-Takayanagi surface, because that's what we expected the error correction, these error correcting codes to do. And so that goes under the name of entanglement wedge reconstruction. So we're going to try to think about entanglement wedge reconstruction in these codes. And the question is, the basic question is, can we take these causal wedges and extend them to a larger wedge, which I'll call E of O. So the causal wedge is always inside E of O. And can we do that? In fact, what we're going to try to do is we're going to try to do that in a maximal possible way. We're trying to extend it as far as we can possibly do. And so in general, for some given code, it's not clear we can always extend it maximally. But what I can do is I can prove some results about when that extension is maximal. Okay, so and you'll see some familiar things. So the first thing that I'm going to tell you, so basically this is sort of the meat of this work. We proved some theorems about this extension. So the first theorem is that the extension E maintains boundary causality. So what does that mean? Well, if I do some extension of O and I also extend the space O prime, the complement region on the boundary, that should always maintain the fact that these two things commute. Okay, this should always be true. And so that's expected just by boundary causality. And it turns out that this theorem, to prove that this is true, you prove something which has a name in quantum error correction, which is called an information disturbance trade-off theorem. And the intuition for that theorem is that there's no cloning in quantum mechanics. You can't take some information and clone it and have two copies of that information. And indeed, that's an essential statement of causality here. There's a precise statement. There's a precise statement, which I think I'm going to skip in lieu of time. But yeah, essentially that's the main point here. The extension maintains boundary causality. Okay, the second theorem that we proved is a version of the JLMS result that I mentioned before. So basically, it's a condition under which you can prove the extension is maximal. So that means that the entanglement wedge for O prime is the commutant of the entanglement wedge for O, right? So remember, in general, we had a subset here, but if the extension is maximal, you can show that that's an equality. And so that equality is the statement of Hague duality. So you can prove the following result. So the extension is maximal, this is the JLMS result, if the relative entropies are equal in a limiting sense. So if I take some bulk state in the Hilbert space, psi and phi, and I map it to the boundary, and I compute the relative entropy reduced to some region MNO, and I take the limit, and I get the same thing as the relative entropy in the bulk. That's very much like the JLMS statement, but it's sort of an asymptotic version of the JLMS statement. Then you can prove these entanglement wedge is maximal. And I'm having a problem with my pen again. Sorry, I hope this is the last time. So yeah, okay. So that's the second theorem that we proved, which is this JLMS result. So that's something that's familiar from gravity, and so that should give some further evidence for the relevance of these codes. Okay. Good. All right. So the final theorem that I might also skip. Well, let me just say it really briefly. Is that once you have an entanglement wedge like this, you have maximal extension of the causal wedges, then you can show that the modular flow of the boundary region maps to modular flow of the bulk. So what is modular flow? Well, it's a special sort of operator, a special symmetry that you get from some algebraic discussions of, that's very natural from these von Neumann algebras point of view. So basically, it's an operator that you should think of. Let's say I did have a tensor factorization, like we had in the original codes. Then it's basically an operator made out of the reduced density matrices. You take the reduced density matrix for the A region, you raise it to the IS, that makes it a unitary. You take the reduced density matrix for the complement region, and you raise it to the minus IS. And that's just the modular operator. Now, it might seem like some weird thing for me to consider, but it really does tell you about a lot about the code. And it also is really important in quantum field theory and studying quantum information in quantum field theory, in particular, the modular operator for a region, which is sort of Rindler space or so for Rindler space is in fact just the boosts in quantum field theory. For a diamond region in a CFT, it's some conformal notion of the boosts. So it's a very specific operator in the quantum field theory. It takes the algebra as well as a state, right? So it's defined in terms of a state and an algebra. And these codes preserve the modular group. Okay, so the proofs of the theorems are a little technical. They require these von Neumann algebras to be something called hyperfinite, which means that I can approximate them by an infinite union of algebras that are finite. So each of these is finite. And you might say that that's quite limiting, but actually it's not. In most of physical applications of von Neumann algebras, they're hyperfinite. So the type 3 von Neumann algebras of quantum field theory that we're trying to get are hyperfinite. So that's not a huge limitation. Okay, so these codes have nice properties. One thing that they're limited by is the fact that basically you have to pick a state and take a limit, and in some sense you're picking some background geometry, and you're just doing small quantum field theory or small perturbations on top of that geometry. Okay, so that means we're going to miss a whole bunch of things in ADS CFT. We may not get black holes and so forth. So really, to understand that, you have to understand different sectors or different large N limits. So associated to different sequence of states, you're going to have different large N limits, and so you get different sort of sectors on which you can do error correcting. And so it's important to study this sort of sector physics, and we have some limited discussion of this. Yeah. And so I'll probably be brief here, but understanding this sector physics is important for understanding phase transitions in the entanglement wedge. These page curve computations, to understand them, that you have to confront this. And in particular, I may or may not, I don't think I'll have time, but this cross product construction of Witten, recent work by Witten, you also have to understand, at least in our language, in terms of this sector physics. So let me mention some results along these lines, and then I'll finish. So the first thing to study is the vacuum sector. So that means a code like this, which has on it a state, excuse me, a state in the bulk-Hilbert space that maps, at least asymptotically, to the boundary vacuum. So this is the vacuum at each end. So there's a sequence of states in the boundary Hilbert space, which is the vacuum, and this bulk state maps to that. Then there's an interesting sort of theorem that you can prove, which is that you would sort of expect the vacuum state to have a representation of the conformal group, right? So if it's a CFT, there should be some representation of the conformal group that leaves invariant this state eta and acts covariantly on the net. And it turns out you can prove that that is true if and only if the entanglement wedges are equal to the causal wedges. So I've defined both of these things for boundary diamond regions. So this is a boundary diamond region. And this is something that we really expect in ADS CFT, and this is something that naturally came out of these codes. And basically the idea for this is to reconstruct the conformal group out of these modular flow groups, the group of these modular automorphism groups that map under the code. Okay, so that's one thing you can do. You can also study thermal sectors, which means you think about where you sort of double your code. So you have two copies, which is like this thermophile double state. And in this, there's a pure state, which is a thermophile double, which if you trace over one of the say the right CFT or the left and right CFT, you trace over the right one, you get the thermal state. And again, for these thermal codes, you assume there's a state that maps to the thermophile double. And as long as there's also a representation of the boundary time translation, so this is boundary time translation, say on the left, and then if there's some representation of that in the bulk for some U of t on the bulk Hilbert space, then you can also prove that the entanglement wedge equals the causal wedge, at least for the entire left boundary. Okay, so now in this is exactly the context that Lou Leuthauser were working, and they made the observation that in this setup, as long as you're above the Hawking-Page transition or some version of the Hawking-Page transition, maybe some Hagedorn transition, then the bulk algebra should be an emergent type 3 von Neumann algebra. And if you're below the Hawking-Page, then you just get the standard thing, type 1 infinity von Neumann algebra. And so various arguments were given in this work, where we have some new argument for this, which is basically if you think about a time shifted state where you time evolve the thermophile double just on the left, then you ask, does this give rise to a new code, different code? So remember, we had these we had to confront the fact that we have different sectors, and so maybe when we do this, we get an entirely new code, and which means that roughly speaking, the sort of code subspaces map orthogonally, so to different parts of the Hilbert space, to different parts of the boundary Hilbert space, at least asymptotically. Then if that's the case, you can also show that the left algebra is a type 3 von Neumann algebra. Okay, so this is another way to think about it. And the basic idea behind this is that the left Hamiltonian the question is that realized in the bulk code? If it's not, then in general, the representation of the time translations that we had, this U of t, has to act as an outer automorphism on the bulk algebra for the left CFT, for the left causal region. And that fact that it's a sort of outer automorphism, which just means that it's generated by an operator that doesn't live on the left, it lives in the full Hilbert space, that actually is a key signature of this type 3 von Neumann algebra. And then let me just sort of finish by saying that, related to this, you can then, if those codes are now orthogonal, you can try to extend the code and put them all together. You have a large code associated to these sort of time-shifted thermal codes, And when you put that together, it's very natural that you get in the bulk something called the cross product of the original type 3 von Neumann algebra. And this was an observation by Witten that now we can reproduce in our codes. In particular, it's an interesting observation because the cross product of the type 3 von Neumann algebra is a type 2 von Neumann algebra, which is something where you can suddenly define entropies. Okay, so let me conclude there. Sorry, let me just make some final comments. So these asymptotically isometric codes are a natural framework for studying ADS-CFT, I think. In particular, they really are a quantum error correcting framework, but they're also a precise one in the sense that you can essentially derive them. They allow for bulk quantum field theory and the interesting effects associated to bulk quantum field theory. We've studied them in some limited settings, in particular different sectors. We studied the vacuum sector and the thermal sector. I imagine there's more applications. As the original motivation was to study energy conditions. I'd like to understand energy conditions in these codes. The split property is some extra property that you usually add, which is interesting and has some interesting physics in ADS-CFT. Okay, so let me finish.